My name is Jay, and I work with my mentor Isaac and Professor Gordon's lab in the Department of Chemical Engineering of the UCB's program. And my project is called Preparation and Characterization of Optically Active Metal Probe for Scanning for Microscopy. And let's get started. So in order to look at nanoscience and nanotechnology, you need instruments that could see at the nanoscale. So how do you see at the nanoscale? Well, let's say you want to look at this nanotip right here. If you're using a light microscope, you could get down to about a micron of resolution. And if you're really good, you can get down to about hundreds of nanometers, but beyond that, it gets blurry because of diffraction of light. So what you could do is use an electron microscope, and notice the scale bars right here. You can get down to about a nanometer of resolution. Or you could use a scanning probe microscope, where you just use a tip that I just showed you, and you just scan the surface that you want to scan, and produce a topographic image. But neither electron microscopes or scanning probe microscopes give you the chemical information that's critical at the nanoscale. So you need a technique that gives you the chemistry and the geometry at the nanoscale. And among these efforts is a technique called tip-enhanced Raman spectroscopy. And I'll tell you how it works. So say you want to see the chemistry at the surface. And what you do is you shine a laser light. And that laser light produces a Raman scattering. This is a change in color. And that corresponds to change in energy. And by measuring the change in energy, you could identify what kind of chemicals are there. But this right here is an example of a light microscope. And you don't get the nanoscale information. So what you do is you bring a tip down, as in scanning for a microscope, and if the tip is just right, then some of that laser light will couple with the electron oscillation of the tip to produce an enhanced field at the end of the tip. And this enhanced field at the end could intensify the local Raman scattering to give you the nanoscale chemical image. But as you might imagine, the critical to this technique is the tip itself. So if you have a blunt tip, you're not going to catch all the details that a sharp tip can. So you want a tip to be as sharp as possible and optically active as possible. And the problem in the field is that it's hard to make these tips sharp and optically active. So how do you make these tips? Well, most practical way is by electrochemical etching, where you dip a wire into a solution of strong acid or base, and you drive a voltage, and that drives an electrochemical direction, one of these right here. And as the etching proceeds, the tip falls down, and then you get a tip like this. Sometimes it's a really good tip, like this one right here, but oftentimes it's not as good. And that's why etching needs feedback, because you want to make good tips all the time and as good as possible. So that's why in my project, the goal is to make a diagnostic tool for etching. And how I'm going to do that is by using a tuning fork oscillator. And the tuning fork oscillator is just like a musical tuning fork you might have played with in elementary school, where you have a tuning fork like this, you shake it on a table, and then it makes a sound. But this one is really small. It vibrates at 32 kilohertz, which you can't hear. And it's a piezoelectric material, so it generates a current that you can measure. And this vibration is dependent on the environment that it's in. So by attaching a wire onto the tuning fork as you're shaking it and etching it, you could detect what kind of forces are present on the wire. And by doing that, we could detect the mass changes, surface area changes, etching dynamics, and hydrodynamic effects that's going on during the tip etching process itself. And this will tell us about, give us some insight onto the tip etching process, and perhaps we could use it as a diagnostic tool for etching, so we can make good tips all the time. Thank you all for listening. I want to give special thanks to everyone in the Gordon Lab and Dr. Erica Lubin, and now I'll take some questions.